Hello and welcome to the 9th Annual Unmanned Showcase, the Future of Innovation, powered by FI. We have a great program this evening, and to kick off the night, I'd like to welcome our Faculty Director, Professor Lee Fleming.
Thank you, Alex. Welcome everyone to the 2020 Master of Engineering Capstone Showcase. This year, we're celebrating our 9th and largest ever graduating class with 479 students and 119 teams. I'd like to think back to our first day in August, orientation, when we filled the entire Poly ballroom in the middle. Now we're virtual. This switch, it highlights but because of the challenges they have faced and overcome. Today, we're going to hear from 9 teams as they showcase their fantastic capstone work. Before we do, I'd like to introduce our donor, Coleman Fung. Coleman graduated from the IER department right here at Berkeley. He was part of the original vision and provided the original backing for the Master of Engineering over 10 years ago. His generosity has enabled much of what you will see here tonight. Unlike some donors, Coleman has stayed very engaged. He's even run many capstones over the years, one of which you'll see here tonight. He's also an avid photographer. All those wonderful pictures in Shires Hall, remember Shires Hall when we got to see each other in person? All those pictures are his. So without further ado, I'd like to turn over the virtual mic to Coleman.
Thank you, Lee. Well, so good to see everyone, or at least meet with everyone virtually. It's not exactly what I had planned, but it will do. Well, let's get the elephant out first. I think with the current pandemic, I hope it will, well, obviously it's so much suffering worldwide, but I hope you guys at the end of the tunnel will actually take advantage of this opportunity to really reflect on what kind of future you want to build for yourself. Looking at how fragile the system is and how narrow focused Silicon Valley has become. The exciting part for tonight is just looking at the projects that you're working on, the diversity and the benefit, the good is so much more inspiring than just the traditional high-tech company, what they are focusing on in the Valley. So I think this is what gets me excited, even though we are going through this challenging time. And I also hope that you have taken full advantage of the MEng program and build stronger and deeper ties to your passions, ties with fellow MEng students, ties to the faculty, because you will need that. You will need these ties when you come out of this pandemic and we build a future that you see fit. Because if nothing else, this pandemic is showing us that we are so much a collective than individuals. And what one group of people do will have great impact or not do. So without further ado, I want to kick this showcase off and let's enjoy the show. Thank you.
Hello, everybody. This is Julie McShane. I'm the Director of Career Development and Alumni Relations. And I just wanted to take this moment to thank our partners. We truly couldn't do it without you. And a special thank you to Blue Goji for your continued support, and to Starkey Hearing Technologies and Asurian for joining our industry partnership program as founding members this year. Both industry capstone partners and capstone advisors tirelessly work to support students both inside and outside of the classroom, and we truly appreciate it. This year, out of 119 capstone projects, we had 24 industry partners advising 33 capstone teams. We're particularly proud of the fact that this year we had 10 MEng alumni advising on partner-led projects. I particularly feel honored and privileged to work with this community. And I want to thank our alumni for your ongoing support, and thank you for joining us this evening. And now I will turn it over to Claire Trias, our Capstone and Student Services Advisor, to review the agenda for this evening. Enjoy the event and the Capstone presentations.
Thank you, Julie. Hello, everyone. I'm Claire Trias, Student Services and Capstone Advisor. Thank you so much for tuning in today. I hope you're all excited to hear from our amazing MEng students, because I certainly am. We have 9 teams. Each team will take 6 minutes to present and 3 minutes to answer audience questions. My colleague Yvette will say a few words about questions. Hello, Yvette. I'm going to take over for Yvette. She seems to be down right now. So the information about questions is to please use the question box on your GoToWebinar interface. Also, please share about the event on social media for a chance to win an Amazon gift card. Coming up next, we're going to ask Priyaj to share his screen as we welcome our first team. And the first team will talk about how they created an inflatable solar array for inland water bodies. Take it away.
Hi, everyone. We are the large-scale solar farming team, and this is our capstone project for the Master of Engineering program. Our project is to develop inflatable modular floating solar array to meet the global energy demand. We are a diverse team of 5 Berkeley engineering students across 4 disciplines. And here is the team. From left to right, they are Arthur from France, Priyaj from India, Gina from America, Roger and I, Jarvis, from China. Undoubtedly, we are living in a world that runs on energy. Global energy demand is over 23 trillion watt-hours. According to the estimation of the International Energy Agency, the global energy demand will increase by 27% by the year 2040. Aggressive policy goals aim for 50% of all energy to come from renewable sources. The annual potential of solar energy is about 96. The annual potential of solar energy is 96 times that of all the coal in the world, and 26 times that of all the oil in the world. We just need to be able to capture it. I will then pass it to my teammate, Roger.
So what is floating solar? Imagine a solar farm that floats. It's all the essential elements of land-based arrays, but it's instead located on top of a water body. It could be floating solar array on a lake or a collapsed coal mine in China. This is the world's largest floating solar array in Huinan, China, with 40 megawatts capacity. And why is floating solar better? It protects water from excess evaporation and prevents algal blooms. It conserves valuable land space. It has lower costs, fast return on investment due to its increased efficiency. It establishes value in unused asset. This makes floating PV an extremely attractive alternative to land-based solar, and its recent explosive growth reflects this. Here's the general layout of a PV system. It's similar to land-based solar systems, other than the fact that the PV arrays and often the inverters are mounted on a floating platform. The DC electricity generated by PV modules is gathered by combiner boxes, the small blue box in the figure, and converted to AC by inverters, the big blue box. The AC goes through the transmission line to the household in the end. The platform, together with its anchoring and moving system, is an integral part of any floating PV installation. And this is the California's largest floating PV plant of 1.8 megawatt. And we had the pleasure to visit this plant and had a meeting with Chris Bartle of CNT Company, the world leader in floating solar right now. Chris explained to us how a floating solar plant is assembled and operated. We learned about the many details and pain points of floating solar. The biggest pain point was the extremely high transportation and installation costs because of the bulky floaters. Imagine the cost of shipping thousands of large air-filled plastic modules. We set out to change this. Now I pass on to my teammate Priyaj.
Thanks a lot, Roger. So based on the market research and the Windsor solar plant visit, we decided to design a robust inflatable floating module that is deflated while transportation and occupies just a fraction of the space. This makes sure that the transportation costs are slashed and in fact, even makes the floater lighter and easier to assemble. Other unique aspects about our design include active cooling using the abundant water resources available to us. And also, as you can see, the cutout sections in the module increase exposure to the water, increasing the convective cooling. This added cooling effect results in an increase of 20% in efficiency of the solar panel. There's also an adjustable tilt angle. As you can see, the panel supports towards the end of the solar panel, they are swappable. What this means is, with the same float, any tilt angle can be achieved. And what this in turn means is that this float can be used anywhere in the world. This float is also modular in design. So one module can link up to form a large-scale solar farm. We decided to build a prototype to display our proof of concept. These are photos from the pre-COVID lockdown era. Meeting in Professor Zodi's lab was so much fun and it was informative. It was great to develop our friendships and camaraderie amongst our teammates. But it was more important to see the different perspectives that each teammate brought from different parts of the world. We also conducted an in-depth economic analysis on a real-life 2.5 megawatt solar farm in Jaipur in India. As you can see, the land-based solar farm costs around $13.8 million, and the generic floating solar with today's technology costs $13 million. Well, if we change this and use our modules with optimized solar panels, it costs almost half at around $6 million. We leveraged the business model canvas to come up with a business model that allows us to go to market and compete with the major players. Our business model includes inflating the solar modules on site where the solar farm is being assembled. Our business model can be tweaked according to local needs such as policy, infrastructure, labor and installation costs, importation and transportation fees. Thank you so much for listening to us. It was a pleasure presenting to you. We are now opening the floor for any questions.
Thank you so much, Team One. So we have a question from the audience for you. How many floating solar farms are needed to supply the global demand?
That's a great question, actually. I have an interesting stat for that. So just in the USA alone, it said that if you cover just 20% of all inland reservoirs, you can supply around 20% of the global of the US energy needs. So that speaks to how much it can be effective. But obviously, you need more technical innovations such as grid balancing and stuff like that for so much solar to actually provide energy to the world.
Thank you. There is another question from the audience. What do you think is the impact on blocking sunlight and on the aquatic ecosystem while using these panels?
Sure, I can take that one as well. So as I said, we need to cover only 20% of the reservoirs. And so the use cases of these floating plants are basically in water treatment facilities or, industrial pools where there isn't really any life in the pools itself. But if it is actually being used in lakes and ponds where there is life, we're not covering too much of the water surface. So it shouldn't create too much of a difference. Additionally, this is a very nascent technology. And so studies are still being converted on a long time scale, and the results of which aren't very apparent yet. So, yeah.
There is a follow-up question. Do you think that these panels are preventing water from evaporating and cause any sort of environmental changes?
I'm sorry, Yvette, can you repeat that question, please?
The question was if you think that these panels might prevent the water from evaporating and cause some environmental effects, which might be negative.
Yeah, actually, this exact effect, it will definitely prevent water from evaporating, but it actually is used in a positive way, such as in vineyards and such as in agriculture ponds. They face a lot of water loss through evaporation. So this, in fact, it helps them prevent that water loss as well. And as I said about the environmental effects, there's still studies going on a very large time scale. So it's not very wise of me to say anything about that right now.
Okay, thank you. Another question from the audience. What is the biggest challenge when it comes to floating solar panels as compared to the ones on land?
I can take that one as well. The biggest challenge would definitely be installation, because there's nowhere the installers can stand on. So they have to balance themselves on small dinghies or boats. That's one of the issues. Other issues are waves. So these floats can undergo a lot of stress because of these waves and relative motion between the floats. So that is another challenge, including corrosion. So we want these to serve a very, very long life, that is around 20 to 25 years. And for that, we need it to be corrosive, resistant to any corrosion, which in itself is a pretty big challenge.
Great. A related question, what are these panels made out of, and how do they withstand extreme weather conditions?
Roger, you can take that one.
The solar panel is made by silicon, polycrystalline silicon. Could you repeat the question again?
Repeat the question. Yeah. So what are these panels made out of? What is the material, and how do you think they can withstand extreme weather?
Yeah, just why I mentioned the panel was made by polycrystalline silicon.
I think it can handle extreme temperature conditions because of the cooling we add. So it definitely drops down the temperature of the solar panels by a lot because of the added cooling effect of the water itself. And additionally, other extreme weather conditions such as wind. So the floats are designed to withhold that much wind and those waves that I said. And another one that I can think of is heavy snowfall. There are actually floating solar farms that have been tested under, I think, 10 to 50 inches of snow, and they were pretty robust even in that case.
Okay, thank you so much, Team One.
Thank you so much for your question.
Coming up next, we're going to ask Liam to share his screen as we welcome our second team. Team 2 will tell us about their design of a wireless communication system for an underwater vehicle. Take it away, Liam.
Our group is the Swarm of Unmanned Underwater Vehicles for Underwater Wireless Communication. Our team consists of Liam Doran, and me, Eric Stern, Anthony Yan, and Ann Shia. We've been working with UC Berkeley's TAF Lab, and I would like to give a special thanks to our advisors, Alex Imas and Professor Reza Alam. Currently, wireless communication allows us to explore the depths of the universe and to send data to our distant planets. Unfortunately, radio frequencies like Wi-Fi and cellular are unable to penetrate water. As such, it makes high-speed underwater communication very difficult. This inhibits undersea exploration and research. Our goal for this project was to develop a network for communication between unmanned underwater vehicles, or UUVs. Our aim was to create a communication that can be embedded into small modular robots called CalSats, which are roughly the size of a watermelon. These UUVs can be linked together to create swarms of underwater vehicles, which can transmit data from deep underwater back to sea level. Our approach to this problem is and another node at the surface of the water. Once completed, chaining multiple together should be fairly trivial. This started with taking a video from a camera that was recorded to a computer. This video is then streamed through Ethernet by first converting it to a modulated laser signal. This signal can be passed through saltwater. Ideally, blue lasers would be used for maximum penetration depth. Once it hits the receiver, it can then be demodulated and converted back to Ethernet, which is connected to another computer. Finally, this can be played back over a monitor. This picture shows our working communication test setup. As shown here, the Ethernet is converted to optical signals and converted back on the receiving end. This allows different computers to send data wirelessly through different media, such as water. The idea is that these lasers can be steered towards the other receiver, which allows each side to move freely.
Thank you, Eric. While the entire laser-based communication system between two UUVs can be quite complicated, I will only be focusing on the feedback control system right now, which is indicated as the yellow boxes in the block diagram. The controller involves a laser and a MEMS mirror on the transmitting end and a position-sensitive device on the receiving end. The pair of two yellow boxes in the block diagram demonstrate that a single UUV is capable of transmitting as well as receiving data simultaneously. Here, next slide is a real-time video that demonstrates the promising performance of the Infinite Horizon LQR algorithm that we developed. We can see the red dot indicated on the PSD jitters back to the center as the reflected angle changes. That is because the PSD records the deviated position and wirelessly communicates back to the controller as an input for the MEMS mirror to steer the laser back at the center accordingly. It is important to note that the feedback control system is two-dimensional. In other words, it is capable to steer not only left and right, but also up and down.
After having designed and fabricated a benchtop test assembly we could use to validate our optical system's tracking and communication abilities, we then approached the challenge of integration. Specifically, for our solution to be feasible, we needed our communication assembly to take up as small space as possible so that it would fit alongside the motors, pumps, and batteries also in the unmanned underwater vehicle. The assembly we designed is modular, inexpensive to manufacture, and sits on a set of metal rails to accommodate lenses of various sizes while maintaining tight tolerances between optical devices. The integrated communication module consists of receiving and transmitting sections to communicate to and from other users. The module itself sits at one pole of the device, transceiving signals across the upper flat panel. Optical components would be controlled by computers and driver boards in the bottom. The hardware controls the device Here you'll see a cross-section of the communication assembly that lets you track the path of the incoming laser passing through the lens, where it is then divided by the beam splitter in order to be read by the photodiode and to be used for tracking purposes by the PSD. The shaded region on the right shows the directional range of the outgoing laser, thanks to the MEMS miracle shown in white. This is useful for keeping track of and communicating with other devices.
Unfortunately, Anne is unable to hear this right now. But
Anne, you're on.
But she's basically going over the part that is we are.
Thank you. I've been unmuted. I'm sorry. So after integrating all components of the full-sized moving CalSat unit, designed a fixed wall-mounted communications unit in order to test two-way communication. We also off-the-shelf and custom-designed components for hermetic sealing, which ensures that internal components are completely sealed from the underwater environment, and that we reduce the number of glued interfaces, which was initially found to reduce the overall lifespan of the product. Next slide, please. On account of recent global developments, our UUV fabrication schedule has been delayed, though we've devised plans for how to manufacture all of our parts once the lab reopens.
Despite the setback on the fabrication, our contribution helped accelerate the merger between UUVs and the complex swarming algorithm that TAFLab has been developing.
Once complete, the low-cost underwater wireless networking will allow for developments in fields such as search and rescue, seafloor mapping, and coral reef maintenance.
By now, we validated our ability to send and receive information at high speeds through water, and we're excited to continue to see this technology take hold and change the way we communicate under the sea. Thank you so much for your time. We have a couple minutes for questions.
Before we take questions, I just want to thank Anne Chia for joining us from Singapore. Thank you so much, Anne. Now on to questions. Thank you, Yvette.
Sure. Thank you, Team 2. So there's a question here about how does the water clarity affect the laser transmission? And also, do you think that any underwater events might disrupt the transmission?
I think I'll be best suited to answer that. Yes, water clarity is a very important thing, but specifically what the more common issue is the clarity of the water and how many particulates are in it. So the idea behind this is that you have a swarm of these vehicles. So in case one gets messed up or damaged, you can have another one come in and take its place. Additionally, because they're swarms, you could actually put them closer together depending on the clarity. So for extremely unclear water, you'd either have to have them very close together or this wouldn't be super applicable towards. But in most cases, there's some level of clarity. So in that case, you can basically ideally group these and distance them depending on how clear the water is.
What about any underwater events that might be disrupted?
So disruptive events, again, they can be, if there's a cutout, they can search and find another one that can take its place. And then basically they can reconnect the stream through different devices that are basically standing in on the side as backups in case the link gets disconnected.
Thank you. We only have a few seconds left. Can you clarify how many devices are needed for clear communication?
So for clear communication, it depends on the clarity and how good of the actual wireless communication system you have designed in it. So for example, let's say if this is working at the clarity that you have specified for about 10 meters, you'd have to have one every 10 meters until you hit the sea floor. But for really clear waters, you can spread them out much further. So it's really, you'd have to dependent on each situation.
Okay, thank you so much, Team 2.
Thanks.
Coming up next, we're going to ask Pierre-Louis to share his screen as we welcome our third team, and unfortunately they can't turn on their webcams. Team 3 will tell us about their work on using high-definition radars to localize autonomous vehicles.
Thank you, Alex. Our team has been working on developing an affordable alternative for autonomous vehicle localization using high-definition radar images. I'm David Scanlon. I'm here alongside Owen Wang, Johan Gerfo, and Pierre-Louis Palacier. Currently, over 94% of traffic accidents are due to human error. There is no doubt about it. We are in need of a solution that is safer, more efficient, and easier to use. In addition to preventing the potential for human error, self-driving cars also provide an average gain of over 50 minutes per day per user. Additionally, they give a new mobility option to over 53 million Americans. Autonomous vehicle companies such as Uber, Waymo, Cruise, and more are in competition to develop the best sensors. And sensors are indeed the eyes of the car, and they allow for multiple tasks such as mapping, localization, environment perception, and detecting. There are currently two main sensors used on autonomous cars. On one side, cameras are a well understood and mature technology that is both reliable and inexpensive. However, they have trouble operating in bad weather and poor lighting conditions. On the other side, LiDARs, or light detection and ranging, have been a default technology used for mapping and localization for current fleets of autonomous vehicles. However, this highly accurate technology is costly and can also break down during adverse weather conditions. So this brings us to the goal of our Capstone partner, Sendar, who's working on developing a radar solution that provides a high precision solution to autonomous vehicle localization that is cheaper than existing LiDAR solutions and that is also weather robust.
So this brings us to the question of our capstone. Can we reach the precision of a LiDAR with the radars from Sendar in localization and mapping tasks? So first, let's have a look at Sendar radar image. So this image, like this one, represents the top-down view of the right side of the car. Each image is issued every 100 milliseconds, and they have a resolution of 1 pixel equal an area of 4 by 4 centimeters in the real world. And with each image, we also have a GPS and orientation information at the top left corner that allows us to position the image in space. So as you can see, the images are very noisy. So the first step of our capstone was to remove most of this noise. So we developed a pre-processing to perform a foreground extraction. That is to say that at the end, we only want to see only the most informative pixel. So the walls, the cars, the trees, and remove all the noise. So the method we develop is adaptive. It means that there is no hyperparameters to tune, and it can adapt to every dataset that Dendar was giving us. Additionally, I said that with every image, we also have a GPS position. But for example, if we are in a tunnel, we can't see any satellites, so we don't have access to this information. So we needed a way to measure additional position and orientation information for image image. So this is possible because if you look at 2 consecutive radar images, there are common parts between the two, and so you can find how to superpose them in order to estimate a transformation between the 2 images and in terms of translation and rotation. This gives us also information on the movement of the car. So we did it with an optimization on the enhanced correlation coefficient that gives an error of 1.3 centimeters in translation and 0.03 degree in rotation. And since for most of the image we still have the GPS measurement, we also developed an extended Kalman filter to fuse the information from the GPS and the information from the ECC measurement to have a very fine position for each image. So having a fine position for each image is very important for our first task, which is mapping. So what is the mapping? We want to create a map, which is a big 2D image of the surroundings of the car. And since the world is not certain, this map is represented by a pair of value and of the pixel value and of their covariance, because we don't know exactly what it is. And when we have a new image, so as I explained previously, we have a precise position of it. So we know exactly where it fits in the map. And so that we have a measurement of some pixel value of the map, Y, alongside with their covariance R, because the images are noisy, as I explained. And then our algorithm to update the pixel of the map is just this one, which is the weighted mean of the previously estimated pixel and the new observed one weighted by their respective covariance. And so the more you see a pixel with different image, the more its covariance will decrease. So this is the results of our mapping process. So the red box corresponds to the area that the car is updating. So on the top of the red box, you can see like new objects appearing. They are not very precise because they are just new. But as long as you go down in the box, this object is seen several times by several images. And thanks to our algorithm, the map is more and more precise. So why also having a map? So it's like in real life, you use a map to localize yourself. So that's the end goal of our capstone, to use this pre-built map with the new radar image to localize yourself. So we also need something more. We need a starting position to know approximately where the car is. And from this position, we can extract an image from the map, which is approximately what the car should see at this position. Then we can compare it with our image alignment method and estimate a new position of the car. And with this new position, we can do a new extraction in the map, compare it with a new radar image, and so on, and localize ourselves. So this is the results of our capstone. So in white, you can see the previously built map. And in red is the new image that the car is seeing and superposed in the map to find its position. So this gives us an average precision of 8 centimeters in position, which is in the range of a LiDAR precision between 5 and 10 centimeters, and even better than most of the GPS that their precision is between 10 and 15 centimeters. So the results of our capstone are very promising, and we hope to see more radar localization in the future. Thank you very much for listening. We were very happy to present, and we have a couple of minutes to answer some questions.
Thank you. So there's a question from the audience. In what way can this increase on-road safety for autonomous vehicles?
So as David said at the beginning, so there are some sensors that are usually used in cars, the autonomous cars, such as lidars and cameras, but there are some drawbacks. For example, there are less precise in adverse weather conditions such as rain, fog, snow. And the radars could provide an additional way to have more information in this kind of situation that will help the car to better understand its environment, and so then take the best decision possible.
Thank you. And can you foresee combining this system with LiDAR or visual approaches in the future?
Yeah. So the goal of developing radar is not to completely replace LiDAR. It's just to provide, as I just said, to provide an additional sensor that could be that could give useful information in certain situation or help in a certain situation. And so that's like the final autonomous cars with all the sensors like LiDAR, cameras, radar is very robust to all the situation, and so then be safer.
And how much or less costly is this technology compared to LiDAR?
So approximately LiDAR is more than $10,000, but there are lots of work to try to reduce the price of these sensors, but they are still expensive. While a radar, so it's more around $1,000, and it's because it's basically the radar technology is kind of an old technology that is used already in plane satellites, and that's why the price is so cheap compared to LiDAR, which is a very new technology.
Great. Are there any limitations of using these radars in comparison to LiDARs?
So they're like, because we had several data sets, so the car was in some situation, and the only limitation we've seen is when the radar is obstructed by an object. For example, if the car is overlapping a big truck, which is made of metal, then the radar is obstructed, so we don't have well-focused images, and then all our algorithm can do anything with it. But then it's like here, for example, if you have other sensors all around the car, maybe you can manage this kind of situation. So this is one drawback, but it's could be better, for example, than a LiDAR, because as you see on the images, a LiDAR will only see the side of the street, while here with the radar, you can even go inside the houses and see some things that won't be seen by an eye or a camera, but that will be seen by the radar. And so it's additional information that you can use to better have an understanding of where you are.
Thank you so much, Team 3.
Thank you.
Coming up next, we're going to ask K-Wei to share his screen as we welcome our fourth team. Team 4 will tell us about how they use augmented reality to visualize travel paths of pedestrians and self-driving robots. Please take it away, K-Wei.
Thank you, Claire. Hello, everyone. We're Team Isaacs. Our project is enhancing semi-autonomous navigation via visualization of human path prediction, which is an open source project to envision new ways for humans to intuitively collaborate with robots using augmented reality technologies. This is our team. We have Xinbei, Gang, Kewei, and my name is Xi. We'll start with problem and solution. In our daily life, you must have seen KiwiBots on campus, either crossing the streets or just stopping at somewhere. Have you ever wondering whether the robot will crash into you? The answer is probably yes, it happens. Not always, but it definitely happens. As we all know, the current level of autonomous driving algorithm is not perfect. However, we cannot blame it all on the algorithm itself, because humans' behavior is so unpredictable that sometimes can surpass the algorithm's predictive power. The question is, how do we make it safer when robots and humans are present in the same physical space? To approach this problem, our team thinks it's time to introduce some human factors in as a robot supervisor. This person will be able to adjust robots' path planning strategy accordingly. We call this semi-autonomous navigation. How do we incorporate human input into the whole process? There are several options. The first option would be to use a binary input. For example, a button that allows the user to start and stop the robot instantly. This is a very simple approach and involves very few cognitive efforts. Or, to be more real-world wise, there is multidimensional control, just like normally how we drive a car. You have the speed pedal, the steering wheel, all these factors affect how the car or robot run. While binary could be too simple and sacrifice safety, and multidimensional could be overwhelmingly manual, we set out to find a trade-off in between, as a control that's both cognitively acceptable and ensure maximum safety.
And then we went off to validate our assumption by building a simulation in Unity 3D. This is our cool menu page and two modes that we will introduce next. Next. The stop mode is a reference that we've implemented in which the user can only have a binary input of stop and resume, while the robot is self-navigating. The user can click on the stop button to stop the robot and resume to continue self-navigation. As you could imagine, this type of control is very limited, and if the user is not responsive enough, the robot is very likely to collide with the human. And then we have the confidence mode. The idea is that we could predict the direction where the human is going. We can have past planning for the robot. However, the degree to which the robot operator trusts the prediction could vary from time to time. So we designed an interface where the user can control a slider bar to control a variable called the confidence level. When the confidence level is set to a high value, the system will generate more aggressive human prediction, leading to the robot taking more affirmative routes. On the other hand, when the confidence level is set low, the human path prediction will be more conservative, leading to conservative path planning for the robot. We used the algorithm developed by Berkeley Robotics Lab to generate our human path prediction. First, the algorithm models the human as optimizing a reward function QH that depends on the human's state and action, as well as a preset destination for human. Using the model articulated by beta, we can generate a possibility distribution for any state-action pair. Beta here represents the rationality coefficient, as shown in the reference image. A small beta value models the human as rational, meaning it will very likely execute the action that maximizes reward, whereas the large beta value models the human as irrational. Any direction is almost equally likely for a given state. We then implemented this simulation in Unity. The colored heat map here around the walking human represents the human path predictions. The deeper the color, the higher the possibility for the human to travel to that position. At a general view, when the distributed color are light and more blocks are present, the direction where the human might go are spread out. When colors become more saturated and fewer blocks are present, very dedicated about which direction to go next. The robot then treats the tiles whose prediction possibility is larger than a threshold as obstacles. With that information, it can generate the shortest path toward the goal point with a star search algorithm. This is the video showing this set.
In addition to simulating our interface in Unity, our ultimate goal is to build this interactive experience in real-world environments. We utilize augmented reality to visualize the human path prediction and robot trajectory. Our system consists of 4 major parts. First, we utilize the motion capture system. The mocap system will broadcast the pose data of human and camera to a computer random ROS system. ROS stands for Robot Operating System. Then, the ROS computer will send the distribution of human path prediction to Unity and render it in the virtual world. Finally, we design a user interface for the robot operator to control the robot behavior by changing the confidence level. So this is the basic structure of our system. In our AR system, we change the 2D heat map to a 3D pillar for showing the distribution of human path prediction. The higher the pillar is, the higher the possibility is. As we can see, in a rational mode, which means the real human motion will completely match the predicted human motion. we will get aggressive predictions. Then in the irrational mode, which means we set it to be in low confidence, we will get conservative predictions. In the end, we also have an adaptive mode. In this mode, confidence level will automatically change in the range based on the actual human motion. Thus, we'll get a prediction that looks like in the middle ground. Thank you very much, and we'll now open up for questions.
Thank you so much, team. So there is a question here. How can you predict where people will walk?
So we use, like we said before, let me change to this slide. So we use this algorithm, and this algorithm will create a human model, and that human model contains the state of the human and the action of the human. And by getting the data from the real human and put all those data into the algorithm itself will get the predictions.
And how can this confidence be applied in cases of high pedestrian traffic?
So here we only discuss about, we only want to see how our user interface will change, will either enhance the safety or not. So our main goal is not really to show it effectiveness in high traffic. So in our experiment, we'll only discuss about how is our user interface work or not, or so we just proposed a new HCI solution. Yeah.
Another question from audience: how would a robot determine a rationality or irrationality of a human's motion?
So the robot itself, it will not determine. So we want the robot operator itself to determine the confidence level. So that's the reason why we put this slider bar here. We wish to add human control and let the robot operator to think, should I consider this situation as irrational or consider this situation as rational, and change the beta value by itself. So, and the algorithm will get this confidence level and just output the predictions.
Okay. And there is a question here about the human controller again. So the human controller is using some basis to set the confidence level. Why can't you develop an algorithm to predict this confidence instead?
Yes. So there's one, I'd say.
We kind of have that algorithm in the adaptive mode.
Yes. So, but when we get these algorithms, so they proposed a way to get a changing beta based on the actual human motion. But from our experiment, we found out that even we use this algorithm, it cannot handle all the unpredictable behavior of the human. Then we want the robot itself, himself or herself, to actually control this beta value instead of using another algorithm.
Okay, thank you so much for your answers, Team 4.
Yvette, we actually have, if there's more questions, we can take one more, if that's okay.
Sure, yeah, we can take one more. So there's a question, is only the position of the human tracked, or is the human's gait also used to determine the next action of the person?
Human position in a 2D map is tracked as an X and Y coordinate, and also the speed of the human is also tracked. These are the two dimensions that we are tracking from the mocap system.
Okay, great. Thank you so much, team.
Thank you. Coming up next, We're going to ask Jessica Elder to share her screen as we welcome our 5th team. Team 5 will tell us about building radiation detecting drones using scintillating materials. Please take it away.
Thank you, Alex. As you so nicely put, our team is going to discuss how we designed a drone with the ability to detect radiation by using scintillating material. I'm Jessica Elder and I study nuclear engineering.
I am Mark Ma from the Material Science Department.
I'm Shubham from the Nuclear Engineering Department.
So accurate measurement of an area's radioactivity is important in many applications, including nuclear emergency response, proliferation detection, and environmental assessments, all of which are crucial for public health and safety. Traditional approaches for detecting and mapping radiation rely on in-person measurement. In other words, trained nuclear personnel need to carry a cumbersome detector, enter the contaminated zone, and get close to the source. The process not only costs time and labor, but also puts nuclear workers at the risk of damaging, even potentially lethal dose of radiations. For example, in the Chernobyl accident, measurements were taken at the severe risk of workers, and the full area of contamination zone was not determined for 10 days, by which tens of thousands were already exposed to deadly dosages. If we can eliminate the need for in-person measurement by employing unmanned platforms, we can remove the risk for red workers while significantly improving the efficiency of the process. As our solution to this problem, we designed a radiation detection system that can be incorporated into a drone. To make the drone lightweight and less costly, a new type of plastic scintillator material is used to serve as both the drone's frame and a radiation detector. As shown on the right side, we replace the feet of the drone with the materials capable of sensing radioactive sources from a distance. The scintillation material is made by mixing 2 aromatic dyes into a polystyrene matrix. The resulting mixture is then polymerized to form a solid that is almost as hard as regular polystyrene, but sensitive to radiation. When the scintillator is hit with radiations, it glows a bluish-purple color, as you can see here.
These plastic scintillator materials have a unique property of converting the harmful invisible radiation into visible light. This visible light travels in the material and ultimately reaches the photomultiplier, or the SIPM as we call them. The SIPM produces an avalanche of electrons when one of these visible lights hits upon them. This avalanche of electrons is then observed as an electrical signal which can be used to identify the type and strength of the radioactive source. Based on the information we shared so far, it would be evident that there are few parameters which can regulate the radiation detection efficiency of the plastic. The 2 most important ones being the length of the plastics and the number of SIPMs. As we saw earlier, the feet of the drone are 16-inch long. So we can replace them with either a 16-inch long plastic or multiple plastics with smaller lengths. Thus, we perform tests to obtain an optimized length and number of SIPM value for our system. The optimization was performed using a combination of experimental and simulation tools. The simulation tool used is called GEONT4, which is a widely used software in the radiation detection community. We developed a code in this software to define the physics of our system and benchmark the code with our experimental data. We performed various simulations using the GEONT4 code for optimizing our detection system. And as you can see from the graph, we observe that the efficiency reduces with increasing the length of the plastic, and it increases with increasing the number of SIPMs. Thus, we concluded that for a higher radiation detection efficiency, our system should be of smaller length with more SIPMs on it.
And as we mentioned, the main goal of our project was to replace structural components of a drone with our radiation detection system. Since this has never been done before, our team created dynamic simulations of the new system to look at potential stresses and deformation that it may experience, and to ensure that the scintillator plastic wouldn't break under normal operating conditions. For example, shown on the top right is an exaggerated simulation of how much the new landing feet will bend under its own weight while in flight. And this simulation showed that the plastic will bend only a fraction of a millimeter. And we also designed new components for the drone, as shown on the bottom right, to ensure that our detection system will be properly connected and incorporated onto the drone. And from these simulations, we found that the plastic scintillator material is in fact mechanically sturdy enough to replace existing components of the drones. As you may imagine, although our project focused on replacing just the landing feet, in the future it will likely be possible to create a drone almost entirely made from scintillator material. Our drone will allow users to quickly measure and triangulate the location of radioactive materials completely remotely. These measurements will be completed faster and cheaper than when using traditional methods of detection, and users will be able to maintain a safe distance from any harmful sources. Moving forward, once shelter-in-place restrictions are lifted, our team will be able to actually test and fly our final product, which we are very much looking forward to. Any questions?
Thank you, team. There's a question from audience. How do you make sure that it is radiation that the device is indicating?
Okay, I can take that question. So, so there's only radiation, the nuclear radiation, the gamma radiations, and the neutrons, which can be detected by these plastics. So these plastics are sensitive only to the gamma radiations or the fast neutrons, which interact with the material of the plastic and produce a light, a scintillation light. I hope that answers your question. Thank you.
It was clarified further. So how do you make sure it's radiation as opposed to UV light or other forms of radiation?
Yes, so the UV radiation does not have the energy range of a gamma radiation. So there's a difference in the energy range. So when we actually perform the experiments, we do get a signal. So we then analyze the signal, and then we get to know the source strength. That is the energy of the radiation source, which basically tells us what kind of source we were looking at.
Thank you. How long can this device work in a hostile environment, such as if there is a Chernobyl-like incident?
So as we mentioned, these plastics are sensitive to radiations. So definitely they do degrade in time, but the degradation time is way longer than we would actually expect. So this has been tested, and so the materials do not have a physical impact of radiation on them. They just get degraded over time, and that's a long time. And that is something which scientists are currently working on to improve that as well.
So will this drone itself be negatively impacted by the radiation?
Can you repeat the question?
Sure. Will the drone itself be negatively affected by radiation?
Not really. Okay.
You can take it, Mark.
Yeah. So the frame of the drone and the electronics, they are quite steady components, and even a Chernobyl level dosage will have very limited, if like no impact on that at all. And our detection system is also quite stable. In terms of a scintillator, a regular dosage, even say like a reactor accident, will not have a big impact on that. It can still function normally.
To add on that, I'd say the drone would stop functioning based on constraints of the drone itself and not the radiation detection system. So the lifetime of whatever a drone is based on its battery life, etc.
Thank you. And how will the color change be observed remotely? Will there be cameras on the drone for a remote observer to see the color change?
Yes. So this system will actually triangulate the location of the source. So this system is actually connected to one of the iPads or any device which we have, wherein it feeds the map of the area, and then it color codes what kind of how much radiation is produced in which area, and then based on that we will get a sense of where exactly the source is coming from.
Thank you, Team 5.
Coming up next, we're going to ask Mary Cruz to share her screen as we welcome our sixth team. Team 6 will talk about the work they've done to advance clinical trials and commercialization of hydrogel that can treat volumetric muscle loss. Please take it away, Mary Cruz.
Thank you, Claire. Hello, everyone. We're Team 6, Hydrogel to promote tissue regeneration for volumetric muscle loss. My name is Zuri. Mary will be our other presenter today, and our other team members are Joe and Clement. So, what is volumetric muscle loss? Volumetric muscle loss, or VML, is a form of trauma in which there is significant muscle loss beyond a critical size that makes regeneration of the wound next to impossible. As a result, there's a lack of full functional recovery of the muscle, and patients with this trauma often face debilitating effects such as falling down often when performing an exercise such as walking. And in the picture above, we have a photo of a patient faced with volumetric muscle loss in their thigh.
So to treat VML, the HELO lab at UC Berkeley has developed a semi-synthetic hyaluronic acid-based hydrogel. This hydrogel is made up of 4 components. We have an acrylated hyaluronic acid backbone, a thiolated heparin, a cell-binding peptide or BSP RGD15 peptide, and a matrix metalloproteinase cleavable peptide cross-linker or MMP. The integration of all these components give this hydrogel its unique regenerative properties. Now, these products can be produced in 3 different forms. We have an injectable microspheres form, a lyophilized or freeze-dried sponge, and an injectable hydrogel. The chemical composition between the 3 of them is exactly the same, but they vary in their manufacturing process, in their final physical form, and also in the mode of delivery. Another thing that is important is that all these 3 different form factors are at different development stages. And we as a team evaluated the maturity of each one of these forms and focused on the ones that were closer to get to the clinic. To do this, as a team, we use something that is called a technology readiness level criteria, which is often used to classify the maturity of new medical devices. Based on this, the injectable microspheres were classified as a TRL2 because this form factor is at an early development stage. Next, the lyophilized sponge was classified as a TRL3 because the proof of concept of this form factor has already been confirmed. And finally, the injectable hydrogel was classified as a TRL4 because there is already enough preclinical data that can be used to support this form factor regenerative performance. The next level is a TRL5, and here is basically where clinical trials are approved. This is very important for the future development of medical devices into the market. FDA has different requirements to give this type of approval. And the team here focused on 2 of these requirements to further develop both the lyophilized sponge and the injectable hydrogel to get approval for clinical trials. The first requirement that the FDA states is that adequate methods, controls for manufacturing, and packaging processes are required to manufacture a medical device that will be used for clinical trials. And the second requirement is about risks. There needs to be data that can be used to demonstrate that the risks of using the medical device will not outweigh the anticipated benefits. Now, Zuri will explain you a little bit more of what exactly our team did in order to further meet these requirements.
As Mary stated in the previous slide, we focused on the injectable hydrogel and the freeze-dried sponge because of their higher TRL level. And I'd like to focus your attention to the column on the left. For both the injectable hydrogel and freeze-dried sponge, we improved manufacturing methods and controls by implementing a process improvement that reduced manufacturing time from 14 days to 5 days. Furthermore, we translated lab protocols into industry-level procedures to ensure consistency in production, and developed an anticoagulant effect assay protocol to assess that the risk of thiolated heparin is not greater than the FDA-approved pharmaceutical heparin. The column on the right shows the work we performed on the freeze-dried sponge alone. So to eliminate risk of infection and further the packaging process, we made sure to identify a solution to keep our sponge contaminant-free during lyophilization and identified a method that will sterilize and keep our components working to pre-sterilization standards. Altogether, the work that we performed this year will bring this therapeutic solution closer to the FDA approval for clinical trials. Thank you. Any questions for us?
Thank you, Tim. So yeah, question from the audience. This is not a drug, but it certainly is invasive. What kind of regulatory challenges do you anticipate?
Yes.
Could you repeat the very first part of this question?
Oh, basically it says this is not a drug, but it certainly is invasive. So it has to go through drug trials. So what kind of challenges do you anticipate?
Okay. Mary, I think if you wanted to go ahead, you could do that.
Yes. There are like certain reasons why we have different form factors. So with the injectable hydrogel, yes, it's a hydrogel that is injected in the area of defect, and getting approval for these type of device, yes, will be a little bit more complicated because there are more components. Let's say with the lyophilized sponge, it will be just a single sponge that can be cut and placed in the area of defect, and that could definitely make the FDA approval process, let's say, easier. So that's why one of the reasons why the team also focused on these form factor, because we definitely think it will make smoother the FDA approval process. And then, as we said, we also work on an assay for the analysis of the thiolated heparin, which is an anticoagulant. And we want to confirm that these modified heparin that we're using is basically, its activity is basically the same as the commercial heparin. And basically, we're looking to provide data to the FDA that is as safe as what is already in the market.
Thank you. Another question. Can you see this technology being used on more sensitive muscle tissues, such as cardiac tissues?
I can take that question. So I think it depends on what form factor we would want to use, because that's a rather invasive procedure, and exactly for what procedure you would be using that for. So that would probably be like some sort of open heart surgery. And in that case, our device would definitely be used to regenerate any defect in the heart. But which form factor you would pick, I think would be a definite question there.
Thank you. Question for time for one more question. Can you speak more about the manufacturing process improvements that you implemented?
Sure.
Yes.
We were able. Yeah, go ahead.
Right. So because originally we developed this hydrogel in a lab procedure, we used dialysis, which is just a purification method, a passive purification method, where we would purify the project using diffusion. But if we want to scale this up just to bring it to clinical trials, we need to make sure that it can be manufactured. So we use tangential filtration flow, which is a filtration process driven by pressure. And because of that, it's a much quicker process. So we were able to reduce the very passive time of dialysis from 14 days to 7 days. And by adjusting our protocol slightly, we were able to get 7 days of filtration down to 5 days.
Thank you so much, Team 6.
Thank you.
Coming up next, we're going to ask Marcel Schacht to share his screen as we welcome our 7th team. This team will talk about using natural language processing to extract information from medical notes. Please take it away.
Yeah, thank you so much, Alex. Yeah, so we are 3 BioE students, Chloe, Lane, and Marcel from South Korea, China, and Germany. So from all over the world, really. And over the past year, we've been building a tool for medical information accuracy. And the importance of this has recently really been highlighted by the rise of the coronavirus epidemic, because there has been an increasing interest in using patient data to model the trend of pandemics, or find correlations between conditions, or even try to predict an individual's health based on their medical history, which is really good for personalized medicine, of course. And to do so, we need large amounts of patient data. And to get access to this data, there is only one slight problem, which is a lot of the patient data is actually in the free unstructured text parts of the medical records, which can be kind of problematic, as this means that the text is actually, the information is hidden to computers, because you actually need structured tabulated data to do predictive analytics. And this is where natural language processing really comes into play, as we can use these tools to extract all the relevant medical information out of the free text doctor's notes and turn it into a structured tabulated form. So there are actually some NLP pipelines already out there. You can look at one here, which is called CLAMP, and you can see that it can identify drugs and treatments or other problems the patient has been subjected to. So now this is all great, of course, but there's one small problem. These NLP pipelines just aren't accurate enough to do reliable predictive analytics with them. And for example, UCSF, who we're working with, uses a pipeline called Apache CTEX, which is one of the most widely used ones, but it runs into some similar problems as other NLP pipelines. For example, it struggles with the ambiguous meanings of words because it's unable to analyze the context of the sentences. For example, the word cold can mean 3 different things. Or also, it doesn't understand abbreviations. And also, what is quite kind of a big drawback is that the output of CTEX is just not really great for analysis for the user. For example, we have one example here, and the first extracted information point is actually incorrect, but the user themselves cannot really see this just based on the output.
Yeah, so here's a brief overview for our project. So first, CTEX will extract the health information from original EHRs, and we display those information to the user through the UI. And then we calculate the NLP metrics to evaluate the precision of matching between the information found in the clinical notes and the information that CTEX has extracted. So the user now can look at the concept and the natural language processing metrics in the UI and provide feedback on whether the extracted information is accurate or not. And those feedback is used as labels to train a machine learning model along with the NLP metrics, which can then identify the inaccurate extracted concepts and compute the confidence score, which are then again displayed in the UI. So in our UI, once you upload the original EHR text files and CSV files returned by CTEX, in the homepage, you can find the distribution of confidence score for each concept, and the frequency of each concept appears. Then if you click on one specific concept, you'll be looking at the original sentence that the concept is extracted from. So by clicking on the concept that's very interesting, you can find more details about this concept, and you will be also in a labeling data page. Now you can label the data, label if the concept is correct or not, and those data will be used for machine learning. So the last step for our project is building machine learning models. We tried for machine learning models to test the performance, and here's an example of random forest. It uses NLP metrics as features, which is X, and the correctness of concepts as Y. And based upon them, it built trees on the information gain. And in the end, we could have a classification result or a confidence score calculated.
So this is the diagram that summarizes our data flows. When the clinical information is shown to a user, then the user gives feedback on our UI system. Then this user-provided feedback data is stored in our SQL database, which then the labeled feedback data along with computed NLP metrics are used to train our model. Then our model computes the confidence score and send this result back to our UI system for our users to see. Moving more closely into our machine learning models, we trained 4 different models where logistic regression and SGD classifier served as a baseline model. Then we evaluated these models using F1 score and accuracy. And as you can see from the bar graph, the random forest showed both the highest accuracy and F1 score out of all the models. So we chose the random forest, our final model, to compute the confidence score. And to summarize, our system focuses on these 4 things to close the gap in using NLP in healthcare. 1, providing different NLP metrics that evaluates the correctness of the output. 2, guiding our users with confidence score with high accuracy. And 3, allowing users to give feedback in a convenient way and using that data to continuously improve our system. So with our predictive tool, when there's another epidemic like coronavirus coming up in the future, we're definitely prepared this time to effectively fight. And we would like to take this project further, so we saved our source code in GitHub. And if you're interested and have any questions, feedback, we're happy to discuss. And now we'll take any questions.
Thank you, team. There's a question here. Does this NLP method still require physicians to manually type out the notes as they're interacting with the patient?
Yeah, sure, I can take this. So there are actually some, so this, what we're building works with input text files. So you would require a text file or like any kind of like typed out note. But there are actually some technologies already out there which do like the automatic transcribing when someone's talking and they write everything down. And then you could use the output of that for as an input for our technology as well.
Thank you. Another question. Have you considered the HIPAA HIPAA compliance for patient data protection?
Yeah, shall I take this one as well? We're closely obviously working with UCSF, who is our industry partner, and they're taking this as well very seriously. So we did all the training on de-identified clinical notes, which does not give any patient information out. And now they're actually in process of launching our system within their own system. So which would mean that, of course, all the patient information would stay within the UCSF system and like physicians that are already dealing with the patient information anyways.
And how would you deal with misspelled words which are frequent in HIRs?
Yeah, I can take this. Oh yeah, go ahead.
You go. No worries.
Okay. I mean, for those misspelled words, we have like Levenstein distance, check the similarity. So we are not only check the similarity among words, we also check the similarity among those letters, like just single letters. So like a portion of misspelled words won't really affect it so much.
Yeah, we created specific NLP metrics which can also deal with misspellings. Yeah.
Okay, great. Thank you so much, Team 7.
Coming up next, we're going to ask Ross to share his screen as we welcome our 8th team. This team will talk about how they designed a system to identify and analyze gait impairment. Ross, take it away.
Okay.
1 in 3 older Americans experience gait impairment. Gait impairments are mostly caused by aging, stroke, and neurodegenerative conditions. Gait impairments make walking and moving around a difficult task, and they affect each individual differently. Currently, physicians diagnose gait impairments by watching an individual walk and then qualitatively assessing different characteristics of their movement. Gait impairments can present in several different characteristics, such as posture and balance, which is how an individual carries themselves and maintains balance, step length and width, including their stance and stride length, circumduction, which is swinging the leg out and around to the side while walking in order to avoid tripping, and this is usually to compensate for being unable to adequately bend the knee or the hip joint, and foot drop, which is the inability to lift the foot, which often results in circumduction as compensation in order to clear the ground. Motion tracking technology can offer some exciting insights into research and clinical gait analysis by quantifying gait metrics like these. Camera systems are the current gold standard for motion tracking. These systems are able to identify a user's joints and capture their gait. This gait information can be used to detect the nuances of each individual's unique walking patterns and guide a more personalized level of medicine.
Okay, yeah, so as Anisha just mentioned, normally I would have everyone direct their attention to my video, but as we don't have video right now, direct your attention to my voice, please. So she mentioned this motion tracking technology really has the potential to improve the space of gait analysis and provide personalized treatments to people who need it the most. Unfortunately, however, this motion tracking technology is not as widely accessible as it needs to be, mainly due to the high cost of the systems, the need for a dedicated lab space, as well as trained personnel to operate the equipment. Our team over the past year, working with Evolution Devices here in Berkeley, California, have developed a system coined GaitTrack. GaitTrack is a wearable motion tracking platform for clinical gait analysis. Our design targets were for the system to be affordable, totally wireless, provide data in real time, and also be user-friendly. In order to drive our costs below that of our competitors, we used off-the-shelf parts for the hardware. A microcontroller is used to process everything, inertial measurement units are used to measure the movements of the lower body, and an RF module or radio frequency module is used to communicate all of this data wirelessly and in real time. Together, we brought all this hardware components to work in a harmonious fashion using our own proprietary circuit boards. So we've designed a system that has 7 of these motion capture devices, and these are the wearable devices that you see on the left side of the screen. Now, this wearable device can fit in the palm of your hand, and we designed a carry case that keeps them protected and organized so they're ready to use when you need them. On the right-hand side of the screen, you can see our flexible straps that are actually used to hold these sensors to the body and prevent them from moving while walking.
Thank you, Ross. So here on the left, we see one of these wearable sensors. So the device simply Velcros onto the band, and then the neoprene is stretched over it and secured with Velcro. So as Ross mentioned, this holds the device snugly to the body, which mitigates motion artifacts. What that means is we don't want the sensor to be shaking while the patient is walking. On the right, we see this in action. These blue tabs are specially designed to provide a comfortable grip while removing or securing the bands. Each device wirelessly transmits data to the computer 40 times per second, which allows us to capture the details of the gait and display it seamlessly in real time. So it looks a bit like this. We have 6 data streams. That's the hip, knee, and ankle angles for each leg while the person is walking. At the end of a test, clinical gait metrics such as step and stride length, dorsiflexion, gait symmetry, and more can be calculated and displayed in a helpful readout. So our system records all the data necessary to calculate these many metrics at this point. It is a matter of formatting this output to generate the readout, which will look a bit like this here on the right. So our 7-sensor device provides gait tracking without the high cost or highly structured lab space or trained personnel required by currently available methods. This quantitative system could change the historically qualitative field of gait analysis.
Okay, and at this time, we'd love to open the floor for a Q&A session. Special thanks to Evolution Devices for working with us this past year to help us develop this system.
Thank you, team. Yes, there's a question here. Would your algorithm be sensitive enough to pick up changes in emotional and mental health?
That's a very interesting question. While we haven't studied the effects of emotional and mental health on a person's walking patterns, if emotional health and mental health did impact their walking patterns, our system would likely be able to detect those changes.
Thank you. And does the, oops, sorry about that. Does the algorithm consider different scenarios such as walking on a level path versus walking on an uphill surface?
So currently our algorithm collects, so the IMUs collect motion data via accelerometer, magnetometer, gyroscope sensors. So it's really just a matter of how we can manipulate that. Currently, our algorithms plot in real time angles of each of the joints while they're walking. And that's going to be true of, whether you're walking on a flat surface or up or downhill. And then beyond that, it's a matter of how you process the data.
And how does the accuracy and reliability of this new wearable system compare to lab-based gold standard motion capture tracking systems such as Vicon Nexus or OptiTrack?
Yeah, oh, that's a very good question.
Should I take this one too?
Yeah, go for it.
So my answer to that is a little disappointing, which is that we wanted to investigate this as a validation test around these last few months with camera systems, but due to the situation, we have not had lab access to these devices. But those tests are absolutely something that is right on our next steps list. Do you guys have anything to add?
That's very well said. Exactly. The next steps are to really validate the accuracy of the system right now. Since we are using off-the-shelf parts, we're using an off-the-shelf inertial measurement unit with pre-programmed fusion algorithm to calculate these angles. And the device itself has been, the one that we are using has been validated previously, and while it does provide quite accurate metrics, it does not compare to the very high level of accuracy that you get from Vicon. That's just not possible using an inertial measurement unit, the cost that we're shooting for.
Thank you, Ross. One more question. Can you elaborate a bit more on how the visualization software works and how it was tailored?
Yeah, you want to take that one too, Haley?
Sorry, what was the last word?
How the visualization software works and how it was tailored.
So currently our visualization is real-time plots that output the angles of each of these joints. So while you're walking, so it starts when you're standing still and all of your angles are at 0 because of our alignment algorithms. And then at that point, once you start running the program and the device, you can see these data streams, which are the angles, change while the person is walking. And that could be in a number of different angle formats. Currently, these plots are axis angles, which means that they're the smallest angle between those two parts of your body for that joint. But we could also output in Euler angles, rotation angles. At that point, it's a matter of conversion.
Okay, thank you so much for the answers. Thank you, teammate.
Thank you very much.
Coming up next, we're going to ask Xiaolin Zhong to share her screen as we welcome our 9th team. This team will talk about how they developed gamified VR exercises to improve health and well-being of older adults. Take it away, Team 9.
$2.1 billion. That is the expected number of people who will be 6 years and older in the year 2050. With all the recent advances in healthcare and medicine, the world's senior population is growing faster than ever. But are we ready for that? Soon, a huge part of our population will face the daunting challenges of aging. However, the current methods for assessing senior health are extremely outdated. These methods are mainly based on qualitative observation by a third party and don't take advantage of any modern technology. In most cases, the older adult needs to go through several repetitive tests while the physician takes notes all the time. This process is slow, inefficient, and often discouraging for the patient, so most seniors end up not taking these tests at all. But how can we change this? Our solution, the Infinity Treadmill, a system that seamlessly integrates virtual reality, treadmill exercise, and health management. Designed by Blue Goji, the company created by Fung Institute founder Coleman Fung, the Infinity transforms the way we measure health. In partnership with Blue Goji, our team developed a collection of virtual reality mini games for the Infinity, which track and evaluate the user's cognitive functions through the games. At the same time, the smart sensors on the Infinity pick up on the smallest nuances in a person's gait pattern. Using all this data, we then create a digital health profile for both patients and physicians. The most important parameter we test for is the so-called dual task cost, an early indicator for cognitive diseases such as Alzheimer's and dementia. But how do you measure the dual task cost? For example, you could first measure your performance for a pure physical task like walking 100 feet. Then you add another cognitive task to your physical task, like walking 100 feet while counting down from 100 in steps of 3. Due to the multitask involved in this step, you tend to lose in performance. And this performance loss is what we call the dual task cost. Now the game development team will explain to you how we integrated the dual task cost into our games.
Thank you, Dennis. And now I'm going to introduce our first game, Sausage Shooter. Sausage Shooter is a first-person shooter game where the user must defend their crops from space invaders. The first cognitive parameter is reaction time. The game logs the amount of time it takes for a user to shoot down a saucer after it appears. The second cognitive parameter is decision making. The player must avoid the yellow saucer and target the blue one. To get dual task cost for both of these cognitive parameters, users play the game with and without walking. We calculate the difference of users' performance under different situations to get the dual task cost. Our second game, Non-Bear, allows users to transform into a bear and walk through our enchanted forest. The first cognitive parameter tested by the game is user's short-term memory. Along their walk, the user will be tasked with memorizing numbers in floating numbers and recalling them shortly after. The second cognitive parameter is pattern recognition. Users will need to detect the pattern on the path and fill in the gaps correctly. Dual task cost is also calculated by having the users complete this task with and without walking. And now I'm going to pass to our data team to talk more about our data collection and data visualization.
Thank you, Nancy. So after our users have used our treadmill, we collect data from 3 sources. Our first source is the game score from our games that we just talked about. Our second source, data source, is the sensor data. As you can see, we have force sensors and pressure sensors on our treadmill, and that's where we'll get our second source of data from. Lastly, we have our body tracking device Connect, which tracks the motions of our joints, and that's our third data source. Once we have all the data in place, we analyze it and visualize it to help the users make sense of it. We have two different dashboards, one for the users and one for the physicians, each customized to help the end user understand the data better. For example, here, this is the user's dashboard. And the first thing you'll see is the overall performance. Here you can see how you've performed in each parameter that we have tested. You can also see your current score, your past average, and your immediate previous score. This helps you keep a neat track of your progress over time. Let's say you're interested in looking at one particular parameter, for example, cognitive. You can see a detailed breakdown of what makes up the cognitive score, and along with that, you can also track your progress over time using our pop-up features. Next, we have a physician's dashboard, which offers a more detailed view. Right here, we have a toggle between single and dual task mode. The dual task mode enables the physician to view dual task performance with respect to single task. This is vital in tracking cognitive impairments. We also have other detailed visualizations, such as this body pixel map that you can see to the left. It tracks the motions of body joints, and each cluster represents the range of motion of that particular joint. Any irregularity here could be picked up by the physicians to further their diagnosis. We have designed many such visualizations to equip the physicians to make the best decisions for the user.
Smart, efficient, and fun. That is how we envisioned the Infinity to be. By gamifying the health testing experience, we hope to revolutionize the way older adults manage and improve their own health. Thanks for tuning in, and let me introduce the rest of my team. We are open to any questions now.
Thank you so much, Team 9. There's a question here. What do you foresee to be some useful industry applications of this project?
I think I can take this one. So BlueGoji actually already implemented the Infinity machine to several facilities, including but not limited to the veteran facility in Los Angeles. There's one Infinity machine in the Nike Jordan store in downtown LA. So it can be implemented in virtually any clinics, physical recovery facilities, and anybody who wants to use the machine to exercise and evaluate their physical and cognitive ability in a single cohesive experience.
What do you predict to be the estimated cost of this system?
So this is still a work in progress, but however, from what we know so far, it is significantly lower than all the traditional big pharma machines to evaluate all the processes. Coleman happened to be in this call as well. I think maybe he can chip in on that as well.
Hi. We actually we are still just building prototype machine. With the pandemic, we have a lot of sort of part issues. I still need to work with my Wisconsin-based OEM manufacturer, so I don't have a number.
No worries. Thank you so much, Coleman. One more question here. What do you foresee to be some major roadblocks for this product?
I can take this question. So, for one thing, our current application focuses more on the analytics side and not really on the predictive side. So we definitely see more potential for future applications that might be a little more difficult to implement, because we want to move from just reading or like measuring the person's health to predicting their health, and that adds another layer of complexity to the entire data collection and data analysis process that we have not yet figured out. So that is like one thing we would like to leave onto future teams or future developers of this project. But also So I guess in regard to the last question, one of the other roadblocks would be the cost of this product, because it is an all-in-one system that integrates physical exercise and virtual reality. So with all the integrated sensors that are implemented in the hardware, the cost of this product is for sure gonna be relatively high, even though we are still sure that it's significantly cheaper than the competitor products on the market. So we think we would focus the rollout of this product mostly with partners, for example, rehabilitation centers, or as Huiqing mentioned previously, like the Nike store, or like other people that are interested in the like physical exercise or health testing experience. And by focusing on these customers that have a little bit more, I guess, leverage in terms of finances, we will be able to roll the product faster, but it's probably still inaccessible for a private customer.
Thank you so much, Team 9.
Thank you, Team 9. And coming up next, I'd like to invite Stephanie Prince, our Executive Director, to share a few words.
Thank you, Alex. Good evening, and thank you all so much for joining us virtually as we showcase the amazing work of our students. We have attendees tuning in today from all over the world, which greatly expands our global Fung Institute community. Each year, the Berkeley MEng program continues to attract top talent from around the world, and today's showcase is a prime example of why. This academic year, our students were met with a great deal of uncertainty, from the fires and the power outages in the fall to the current pandemic crisis. Our students rose to the occasion, showing great leadership, innovation, resilience, and excellence. So to you, Berkeley MEng class of 2020, you are the leaders this profession is calling for, and congratulations on a job well done. Tonight, I have the pleasure of introducing our esteemed leader for the College of Engineering, Dean Tsu-Jae King Liu. Dean Liu is internationally recognized for her innovations in semiconductor devices and technology. She has authored or co-authored more than 500 publications. She holds 96 patents. She is a fellow of the Institute for Electrical and Electronics Engineers and the National Academy of Inventors. She is also a member of the National Academy of Engineering and the Silicon Valley Engineering Hall of Fame. So ladies and gentlemen, please welcome with me, Dean Tsu-Jae King Liu.
Thank you so much, Stephanie. Good evening, everyone. Really my pleasure to join you all this evening. As you know, typically at this time of the year, this MEng Capstone Showcase is held in person. We have usually over 100 teams, really exciting disciplines showcased, and a lot of innovative, interactive presentations. And unfortunately, due to the circumstances this year, we have had to pivot to an online showcase. And I'd really like to thank you all for adapting with us to this new normal. And I'd really especially like to express appreciation to the staff of the Fung Institute for making this event possible. Well, tonight's teams are just a sample of the 119 projects that the Master of Engineering program oversaw this year. And the 8 teams that presented tonight represented students from each of our 7 College of Engineering departments. The wide range of projects that presented tonight certainly showcase the best of Berkeley, and really just showing how we innovate for the greater good of our society. So from inflatable modular solar arrays to what we just saw with Gamified our VR exercises to improve senior health, you really have demonstrated how Berkeley can make a positive impact in the world, and how we combine innovation and leadership to achieve that goal. So I'd like to congratulate all of the MEng students. I hope to see you online at the online celebration for all 2020 Berkeley Engineering graduates, and congratulations to all of you for your achievements to date. As you go off into the world, we hope that you will continue to advocate for our public mission to innovate and to lead for the benefit of for a brighter future for all. And thank you very much. Go Bears and Fiat Lux.
Thank you, Dean Lu. And now a few words from Walter Campbell, who's been our video editor this evening. Walter?
Hi, everyone. I just wanted to say really quickly just how much of an honor and a privilege it's been to share the virtual stage with our students tonight. And yeah, it's just been really inspiring, and it really just makes me feel better about the future. So thank you again.
Thank you, Walter. Also, many thanks to Ashley Villanueva and her incredible team, who, among other things, created the 2020 Capstone Showcase website that features all 119 teams. Please visit the website. In about a week, we will share videos, project briefs, and our Capstone Award winners. Many thanks to everyone who made this event possible. Claire, Yvette, Julie, Yuhi, Beth. There's been a bunch of people on the line to deal with contingencies. And the biggest thanks goes to our presenters. I'd like to point out something that may not be visible at the first glance. I believe 6 out of 9 projects presented today had a hardware component. Everyone's been really hit by the shelter-in-place order. Teams that have been working on projects involving hardware had a unique set of challenges. They made incredible midterm pivots to bring their work to a meaningful conclusion. And this, among other things, shows a remarkable level of engineering leadership. And that's what MEng is all about. Thank you. Have a good night.